Good evening, everyone. So in this class, we'll be discussing on some of the problems of electric field intensity. In the last class, we discussed about the electric field due to point charge, and we also calculated the vector form of the electric field due to a point charge. And so today's class will be totally based on some problem discussion based on the previous topic discussed. So we'll be starting with this question number 1 here. The question number 1 is that a charge Q is uniformly distributed over a ring of radius R. We have a ring. The radius of the ring is R, and we have distributed charge plus Q on this ring. If a small portion of length dl, the portion of length dl is removed from ring, then we have to find the electric field at the center of the ring, and we will also try to look for the direction of this electric field intensity at the center of this ring. And suppose that if the ring was complete and there was no portion removed from this ring, and this plus Q charge is distributed uniformly over the ring, it means that all the electric field vectors due to the elemental ring, elements of a ring, like we have this element dl here, and suppose that the charge because of this element is dq, and the electric field because of this element dq, because of this point charge dq, will be towards the ring like this. And similarly, if we have another element like this here of length dl and charge dq, the electric field vector because of this charge dq will be radially towards the center of the ring. And we can see that this electric field is opposite to the previous one. So it is going to cancel the electric field because of this charge dq here, and the electric field because of this charge dq here is going to cancel out. So it means that if this plus Q charge is uniformly distributed on this whole ring, then the electric field at the center will be zero, because all the electric field vectors will be cancelling out each other and there will be no net electric field at the center of this ring. And we can also understand this by suppose that, but in this case, we have been given that it's not a complete ring. A small portion of ring has been removed. So ring is like this, and a very small portion. The radius of the ring is R, and very small portion like dl, this has been removed. And let's suppose the charge of this dl be dq. So what we can do is that suppose that if we want to calculate, if we want to complete this ring so that the system does not change, what we can do is that if we add a plus dq charge at this place and also add a minus dq charge at this place, then once again the total charge because of the plus dq and minus dq, it's going to be zero. There is going to be no change on the system, no change in the charge on the system. So system will still remain the same. But what happens is that because of this plus dq and rest of the charge on this ring, because of this plus dq and rest of the charge on this ring, the electric field at the center is going to be zero. It means that there will be only electric field at the center because of this minus dq charge. Because of this minus dq charge. So only minus dq charge is going to contribute to the electric field at the center. So only minus dq charge will contribute the electric field at the center. And assuming this dl length it's a very small portion, right? So this dq will be like a point charge. The electric field because of this dq charge will be the same as that of the electric field due to the point charge. So direction of this electric field vector because of this negative charge will be towards this negative charge, and it will be like this. So this is going to be the direction of the electric field, and it is a small electric field. Let's suppose that this electric field is TE, and this electric field will be because of this dq charge. So it's going to be k dq upon r square, where r is the radius of this ring. And we know the total charge because of on the surface of this ring is plus q. So if we define a charge density, linear charge density lambda, that's going to be plus q upon 2 pi r, which is the circumference of this ring, plus q upon 2 pi r. So this lambda is a linear charge density. It is dq upon dl, that is plus q upon 2 pi r. So our dq charge is going to be equal to q upon 2 pi r multiplied by this dl. So we can just replace this dq here. The electric field because of this ring, this portion of ring, it's going to be k q dl upon 2 pi r. So this is the electric field because of this portion of a ring. So this is the electric field because of this removed portion of the ring, and it will be towards this orifice because the charge is negative. So let's move on to the next question. The next question is that we have two charges plus q and plus q. Two charges plus q and plus q. Let's suppose we have two charges here, plus q and plus q. And this is origin O, and this plus q charge is placed at a distance of a. The coordinates of this charge is a comma 0, and the coordinate of this charge is given as minus a comma 0. So it means that plus q charge is placed here at minus a from the origin, and this plus q is placed at plus a from the origin. So there we have a point here P whose coordinates are 0 comma r, 0 comma r, which is perpendicular to this line joining plus q. We have to find the electric field intensity, how the electric field intensity is going to vary with r, and also we have to plot the electric graph between electric field intensity and the distance r. So at this point, the electric field intensity will be both because of this plus q and this plus q. So electric field intensity because of this plus q charge is going to be in this direction, away from this charge. And the electric field intensity because of this plus q charge, it's going to be in this direction. So this is the direction of the electric field intensity because of this charge. And let's suppose that the distance from here to here is nothing, it's a, and from the distance here to here, it's also equal to a. And the point P is at a distance of r from this point O. So this hypotenuse here will be nothing, it will be equal to under root of a square plus r square. And this will also be equal to under root of a square plus r square using the Pythagoras. So let us suppose that the electric field here is E, and the electric field is here is E2, and this is E1. The magnitude of this E1 will be nothing, it will be kq upon distance square, that is a square plus r square under root whole square, and E2 will be once again this kq upon under root of a square plus r square the whole square. So from here, our E1 will have a magnitude equal to E2, that is equal to KQ upon A square plus R square. So this is the magnitude of E1 and E2. E1 and E2. Let's suppose the angle between these two vectors E1 and E2 here is theta. This is the angle between E1 and E2. And if the angle between these two vectors here is theta, then this angle is also going to be, complete angle is going to be theta, right? And this will be a half angle, that's theta by 2 here. And this will be a half angle, that's theta by 2. Theta by 2. And we know that when we have two vectors at an angle of theta, but both the vectors are having the same magnitude. But both the vectors are having the same magnitude. If we have two vectors A and B, two vectors A and B, and if the mod of A vector is equal to mod of B vector, then we know the resultant of these two vectors is given as, that is 2A cos of theta upon 2, where theta is the angle between these two vectors. Similarly, we have here two electric field vectors E1 and E2 at an angle of theta, but both the vectors are having the same magnitude. So we can write the resultant of these two vectors as E is equal to twice E1, or E2 we can also write cos of theta upon 2. Cos of theta upon 2. So E is equal to 2 times KQ upon A square plus R square into cos of theta upon 2. Cos of theta upon 2. Now from this triangle we can calculate the cos of theta upon 2. The cos of theta upon 2 will be nothing, R upon under root of A square plus R square. So cos theta upon 2 will be nothing, it will be R upon under root of R square plus A square. So we can substitute the value of theta upon 2 in this equation. So it will be twice KQ upon A square plus R square into R upon R square plus A square raised to power 1 by 2. So finally the electric field intensity at that point is going to be just a minute. So it's KQR upon KQR upon A square plus R square raised power 3 by 2. So KQR upon A square plus R square upon raised power 3 by 2. So this is the electric field intensity because of these two charges at a point P. We can see that the electric field varies as a function of R. Now we have to plot the electric field, this electric field intensity. We have to plot this electric field intensity because as a function of R, as a function of R. We have to check how the electric field intensity varies as a function of R and try to plot it in both the quadrants, in the first quadrant as well as in third quadrant. Means for plus R, when the electric field is measured above this line, and also when the electric field is measured below this line, how this electric field intensity is going to vary. So we'll try to solve it. So here's a factor of 2. Let me take a Cartesian system here. Why explain? This is the why explain here. E versus R. We have to plot E versus R. We can see that, suppose that when R is very closer to the origin, and the distance R is small, means that R is much less than A. R is much less than A. So it means that if R is much less than A, we can neglect the value of R as compared to A and try to see how this electric field is going to behave at the origin. So E comes out to be twice KQ R upon, so it will be A square. We neglected R square as compared to A square, so A square raised to power 3 upon 2. This 2 and 2 will get cancelled. So we'll be left with twice KQ R upon AQ. So we can see that here 2KQ upon AQ is a constant. So E is directly proportional to R for smaller distance. For smaller distance, when R is very less than A, very less than A, then E is directly proportional to R. We know that it actually mimics the behavior of y is equal to mx. Y is equal to mx, and it is a straight line equation, right? So it means that the electric field intensity, the electric field intensity will be behaving like a straight line when it is measured close to the origin. When it is measured close to the origin, so it means that it will be like this when it is measured close to the origin. So it will show a straight line behavior close to the origin. For a shorter distance, the behavior of this electric field intensity will be a straight line behavior, right? But if the distance is larger, means that R is much greater than A. For the larger distance, how this electric field intensity is going to behave. Let's suppose that R is much greater than A. If R is much greater than A, E is equal to twice KQ R upon A square plus R square raised to power 3 by 2. So R is much greater than A. So we can do one thing. We'll get R square common from here. If we take R square as common, so square of there is a whole power of 3 by 2 here. So it means that we'll be getting R cube here. It will be R cube here, and we'll be left with 1 plus A square upon R square raised to power 3 upon 2. 1 plus A square upon R square raised to power 3 by 2. So this is the behavior when R is much greater than A. So we have taken R square here common. When R square is taken common here, this is what we are left with. So it will be 2ice KQ R. It will be R cube 1 plus A square upon R square 3 by 2. But A square here is much less than R square. A square here is much less than R square, or we can say R square is much greater than A square. So we can neglect this term here. But this term will approach to 0 here. This term is going to approach 0. So we'll be left as E as 2s KQ upon R cube or 2s KQ upon R square. So it means that as R tends to infinity, R tends to infinity, the electric field intensity is going to die. The electric field intensity at the larger distance or the infinite distance will be 0. And we also see that the electric field intensity at the smaller distance increases at first. and then it goes to zero. It goes to zero at infinity. So it means that if the electric field intensity is increasing first, then goes to zero at infinity, then it must be maximum at some point between zero and infinity. Then it must be maximum at some point between zero and infinity. So the behavior of this electric field intensity as a function of R will be like this. At some point there will be a maxima. There must be a maxima, and then it will come back, and the intensity of this electric field will decrease, and it will go zero. It will go to zero at infinity. And same behavior it will show on the negative R. It will be increasing, and it will be maximum on the negative side, and then it will be decreasing to infinity at as R tends to minus infinity. So as R tends to minus infinity, E tends to zero, and similarly as R tends to plus infinity, E once again tends to zero. E once again tends to zero. We can also find out that at what point there is a maximum value of this electric field. For that, what we have to do is that we just take the derivative, that's d upon dr, and substitute the value of this derivative equal to zero, and then check at what point it is going to show the maximum behavior. At what point the electric field intensity is going to be maximum. We just have to take the derivative of electric field with respect to r and put that equal to zero. So that's it. That was the plot between electric field and this position vector. And let's discuss the next problem. We have been given four situations here. Figures below show regular hexagons. Four hexagons are given here with charge at the vertices. In which of the following cases the electric field at the center is not zero? In the last class, we discussed that if there are n number of charges, n number of equal charge. By n number of equal charge means that they should be equal in magnitude as well as in sign. Means if there are n number of positive charges equal magnitude, or n number of negative charges of equal magnitude on the corners of a regular polygon, then the electric field intensity at the center of that regular polygon is always going to be zero, be it triangle, be it square, be it pentagon, or any other regular polygon. If n number of equal charges are placed on the corners of a regular polygon, then the electric field intensity at the center is going to be zero. So we have been given four cases here. In the first case, we can see that Q, and Q, all the six Q charges are placed at the six corners of this hexagon. So definitely in this case, electric field intensity at the center is going to be zero. Let's look at the second case. Plus Q charge, plus Q charge, plus Q, and then we have minus Q and minus Q. Now we can see that the electric field intensity is not going to be zero because now at some corners plus Q charge is placed, and at some corners negative minus Q charge is placed. So electric field intensity in this case is not going to be zero. It will be a non-zero quantity. So let's try to see at the third case. Now, at the third case, we have 2Q, 2Q, Q, 2Q, and 2Q on the six corners of hexagon. Let's suppose that this 2Q charge we can split into as Q plus Q. And this charge we can also split into as Q plus Q. Now we can read it like this. We have 6Q charge at the corners, then 2 extra Q charge at the two opposite corners. So the electric field intensity because of this 6Q charge will be zero, but we'll be still left with 2Q charge, 1Q charge here at this corner and another Q charge at this corner. But once again, if we look at this, these two charges are still diagonally opposite. So electric field intensity because of this Q charge will be in this direction, and the electric field because of this left Q charge will be in this direction. It's still going to cancel out. So once again, the electric field intensity is going to be zero. So this is the case where even if an unequal charges are placed on the corners of a regular polygon, but still the electric field intensity is going to be zero. The still electric field intensity comes out to be zero. So let's try to look at this case 4. Case 4. We have 2Q charge here 2q charge, and we have again 2q charge here, and these are the four charges q, q at this point, at these four corners, and 2q charge once again here at this corner also. So what we can do is that we can once again split this case for like this. We can draw a hexagon here. Like we have 2q charge, q charge, and 2q charge, q again, and 2q, and q here. Let me just draw this hexagon again here and try to modify it a bit so as to understand it, what is actually happening. I can split this 2q charge here as q comma q, and this is the q charge. I can once again this 2q charge here as q comma q. So we have q here, and once again q comma q. The system is not going to change. System is not going to change. Now let's look at it. So because of these six q charges, the electric field is going to be zero because of these six q charges. Because these are the six charges at the corners of regular hexagon, but we are still left with three q charges here. This q charge, this q with the yellow, and this q with the yellow. Electric field intensity because of this q will be in this direction, and the electric field intensity because of this q will be in this direction, and the electric field intensity because of this will be in this direction. So length of each of the vector is same, but they are at an angle of 120 degree each. At an angle of 120 degree each. 120 degree each. So once again, because of these three charges also, electric field is going to be zero. It means that the net electric field, because of all these charges at the hexagon, is going to be zero. So it's once again going to give zero electric field. Uh, let's try to discuss question number 4 here. The question number 4 is four charts are placed on the corners of a square as shown in figure. Side of the square is 5 centimeter. If Q is in 1 microcoulomb, then electric field intensity at center will be. Then the electric field intensity at the center will be. Where to find the electric field intensity at this center of this square? At the center of this square. So we'll just draw a square here. So this is the square. We have Q charge minus 2Q charge and minus Q charge here and plus 2Q charge here. The side of the side of this square is given as A is equal to 5 centimeter. And the value of Q charge is given as 1 microcoulomb. 1 microcoulomb. It's given as by 1 microcoulomb. This is the center C. At the center, we have to find the electric field intensity. We have to find the electric field intensity due to all of these charges. The electric field, because of this charge, minus Q will be in this direction. Let me denote it with A, B, C, and D. The electric field, because of this minus Q at A, is in this direction. And this will be the direction of the electric field due to this minus Q charge. And this is the direction due to the electric field at plus 2Q at B. Let me call this as A1, this is A2, and this is A3 here. And this electric field, because of the charge placed at corner D, let's suppose that its value is E4. And this is the side A. We know that distance between the corner of a square and the center of the square is nothing. It's the A upon root 2. This distance, this length is nothing. It will be A upon root 2. A upon root 2. E1 and E2 electric fields are opposite to each other. E1 and E2 electric fields are opposite to each other. So E1 and E2 are opposite. So they'll cancel it. E1 and E2 are opposite. Let's try to find the resultant of this E1 and E2. E1 and E2 are opposite to each other. So the resultant of E1 and E2, they are opposite to each other. It will be E1 minus E2. E1 minus E2 or E2 minus E1. Because the charge at C is greater than charge at A. So we'll be doing E2 minus E1 here. So it will be twice KQ upon A by root 2 ka whole square minus KQ upon A by root 2 ka whole square. We'll be left with KQ by KQ upon A square multiplied by the 2. So this is the net electric field because of this E1 and E2, and it is equal to twice KQ upon A square. It's equal to twice KQ upon A square. And similarly, because of the charge Q and plus 2Q at D and B, the net electric field will be along B. We'll be doing E3 minus E4 E3 minus E4, that's twice KQ upon A by root 2 whole square minus KQ upon A by root 2 whole square. So we'll be left with KQ 2 times KQ upon A square. Now these two electric fields are now in this direction. So this electric field will be in this direction, and its magnitude is once again equal to twice KQ upon A square. So these two electric field vectors are now at an angle of 90 degree with each other. At an angle of 90 degree with each other, but magnitude of both electric field vectors is equal once again. So we'll be using the same formula. We'll be using the same formula of the vector addition, that if two electric field vectors are at an angle of theta of equal magnitude, we'll be using 2 even cos theta upon 2. So twice 2 kq upon A square. The angle between them is 90, so it will be cos 90 upon 2. So it will be 4 kq square, kq upon A square, cos 45, that's nothing, that's 1 upon root 2. So it is 4 root 2 upon 2 kq upon A square. So finally, the final answer for this question will be 2 root 2 kq upon A square. Kq upon A square will be the final answer for this question. And this fifth question number 5 is once again the same as we discussed in the question number 1. Now here we have been exactly given, but in this question we have been exactly given the length removed from the ring. In the previous question, if you can look at the question number 1, solution of the question number 1 right here, the final answer we got was the electric field because of this removed portion was kq dl upon 2 pi r. So we can directly use this equation here, try to find the magnitude of the electric field here. So the electric field, small electric field because of this removed portion will be, if the portion was not removed and this plus q charge was uniformly distributed on the ring, then the electric field at the center would have been 0. So that's T kdl into q upon 2 pi r. 2 pi r, then there should be a r square factor also. There must be r square factor. So in this question, we wrote that dq is q upon 2 pi r into dl, right? And we actually missed a factor of r square here. So there must be a factor of r square here. Otherwise, it will be a dimensionally incorrect. See, we actually missed r square factor here. We can see that if we do not use the r square factor, then definitely it's going to be dimensionally incorrect. So our dE will be kq multiplied by dl upon 2 pi r cube. So this is the correct relation here. So there is a 1 upon r square factor here. So we'll be left with kq dl upon 2 pi r cube. Now in this question, the gap is of 0.02 meter. So we can directly substitute the value of dl as 0.02 meter, or we can write it 2 into 10 to the power minus 2 meter. And the value of charge q is given as 1 coulomb. We can substitute the value of 1 coulomb. And radius of this ring is given as 0.5 meter. It's given as 0.5. We can use the value of k as 9 into 10 to the power 9. And dl is given as 0.02 meter. And q is 1 coulomb upon 2 pi r cube. That's 1 by 2 ka whole cube. So from here you can get the final answer for the electric field intensity because of this removed portion. So that's it for today. In the next class, we'll be discussing about the properties of the electric field lines and the electric field lines also. And also we'll be discussing some of the basic concepts of plotting the electric field intensity due to different combination of the charges that we'll be doing in the next class. So till then, take care and goodbye.